Hello, everybody. What we're going to be doing today is going over some of this programming number two assignment. Now, I know that most of you finished this, or not finished this, but got close to finishing this in class, but not very many people have turned this in yet. And some of you may be working on this at home and you got stuck and you don't know what to do next. And so I'm going to go ahead and post this today. I know that it's supposed to be due today, but if you turn in your assignment, next week or something, you're still going to get full credit. Don't panic about like when you get this one in. Okay. Um, Now, having said that, I think I just want to get right into it and get started on this. I'm looking at programming two here, and there's a PDF, and also there's the homework two zip file, and I've got those both saved already in a folder here. So I've got my zip file and then I've got my PDF. So I've got the PDF open here so we can read the assignment. And also I've got Overleaf website right here. And that's so I can, edit it as we go to show you how to turn in your work if you're having trouble. So I'm going to change this and zip file name here to tutorial on the end. That's not what I wanted. I wanted this changed to tutorial. Okay. So that's just the zip file from the assignment. And in Overleaf, I'm going to go to new project and upload project. And then I'm just going to drag this zip file right over into Overleaf. And, there's the same file that we were looking at. That's just so I can maybe put some answers in here as we go in case people were having trouble with that. Now let's look at the actual assignment here. The idea behind this assignment, which I mentioned in class, is that we don't really have new programming to do in the book yet, not until we get to chapter three, which will be soon. Um, but we still needed to have some kind of programming work to do in the lab. And so we're just doing sort of generic programming exercises from this Project Euler website, which you can look up. Now, if you've never looked up Project Euler before, if you Google any of these, like Project Euler Problem 1, you will find, well, first of all, you'll find the site where the problems are, but also you will find many solutions. Um, so these are very, very Googleable if you're trying to figure out how to do any of these problems. Um, Having said that, let's just let's just actually do some of these. So this first one, I think we'll start. I think we'll start here. This is very similar to a previous assignment, I think, where we had to check if something is, multiples. Um, so we'll do this one, I think, in its entirety to just to get started, get warmed up, I guess. So Project Euler problem one. What are we supposed to do? What does it say? The sum of multiples of 3 and 5. Yeah, here it is. Find the multiples of 3 and 5 below 1,000 and add them up. This is a very simple thing to do. It's just we're going to do it in like a for loop type thing. So I've got this. I'm in Octave. I've navigated to the folder that I have set aside for programming 2. You can put a folder on your desktop and navigate it to that. You can navigate to that folder if you want to, something like that. You need to know where your files are. Then in the editor here in Octave, I'm going to start my code. So here's what I think we should do. So let's look here. The sum of all multiples of 3 and 5 below 1,000. Now you can hard code this. You can hard code this to 1,000. I like to put something like this in equals 1,000 at the top, so I can sort of change it and have the results reflected in my answer without having to change it in the number in multiple places. So the easiest way to do this is going to be we need to loop from all the numbers that are below 1,000, which I'm calling n. So the way to make a loop from 1 to 1,000 in Matlab is for I equals 1 to 1,000, like that. Or in this case, 1 to n. And then we want to check if the number is a multiple of 3 or 5. Well, we know how to do that. We've talked about this. If you do mod the number and 3, if that's 0, it's a multiple of 3, right? So this right here is only going to, this statement is only going to be true if the number is a multiple of 3. If I go back to the command window, you can see that I can just type right here. Sorry, I was running a bunch of other stuff earlier. So if I do like mod 12 comma 3, the answer is 0, right? If I do mod 12 comma 3 equals 0, then we get a 1. So that's telling me that it's 12 is divisible by 3. If I change this to a 13, I get a 0 because 13 is not divisible by 3. If I put a 14, I get a 0 because 14 is not divisible by 3. And if I put 15, I get 1 because 15 is divisible by 3. So this is how you check divisibility in Matlab in a pretty easy way. So this would be to check if I is divisible by 3. Now, there's lots of ways you can do this. Either with one if statement, you can say if this is true, then something. According to the problem that we're solving, we're looking for multiples of 3 or 5. The way you would do that is if mod I comma 3 is 0, or, and then we'll just copy this, I comma 5 is 0, then we do something, right? Now, if you're copying this for MATLAB, notice that Octave added an end if to end the if statement. You can end that with end if or just with end. MATLAB requires end. Octave is okay with end or end if. So I'll just change it to end. It doesn't matter. So where we are now, line 5, we get here if the number I was divisible by 3 or by 5, right? So we're looping through 1, 2, 3, 4, 5 up to 1,000. If it's divisible by 3 or 5, you end up here at this line. Now, what are we supposed to be doing with the numbers? Well, according to this, we are supposed to be adding them up, the sum of all multiples of 3 or 5. So we need a variable to keep track of our sum. I usually use s. So that's our sum. And then here, line 6 now, is where we're going to add our number. So you just do s equals s plus I. And we only do that line 6 if the if statement evaluated to true, which will only happen if the number was divisible by 3 or 5. Now, I've ended the if statement. Now I'm going to end that for loop, and this should be it for this problem. So I'm going to save this. This is problem 1.m. I usually just save it with the problem number, easiest way to do it. So like a way to test this, that it's working before we go up to 1,000, is they show you an example, right? They say if we list all the natural numbers below 10 that are multiples of 3 or 5, we get 3, 5, 6, and 9. The sum is 23, right? So to check your work, you can come here, change this to a 10, save it again, and we'll run this. There's a run button right here, or from the command window, I can type prob1. Now, we just ran it. Nothing showed up on the screen, which, of course, nothing showed up on the screen because in my code, nothing was set to show up on the screen. You can just do this, just type S, and it will show on the screen. Or I can do like display S like that, and it will show up on the screen. So I'll save that, come back here, run this again, and this time it says 33. Is that the right number? Let's check. The sum of these multiples is 23. Uh-oh, what happened? Right? So we have to do a little bit of debugging here. Um, yeah, I guess we do. So let's do this. So to debug this, let's put like an I here and save this, run it, or I ran it again, but prob1, run it. It says 3, 5, 6, 9, 10. 3, 5, 6, 9, 10. So we got an extra 10. Why do we have an extra 10? Um, it says find all multiples of 3 or 5 below 1,000. Oh, okay, I see. Because we were listing numbers below 10, and 10 is not below 10. So if I change this to a 9 now, that's what matches the example in the PDF. So if I save that and I run it, this time I get 23. Okay, so it's working fine. So the code is working fine. But that does show us an important thing, and that is um, if you put 1,000 here, right? Actually, we need 999 because uh, this says specifically below 1,000, not equals 1,000. So I'll use 999. The alternative is to leave that 1,000, but then to change this to in -1, so it's below. Either way, one of these will work. So I'll just save this. We come here, we run our code. It's spitting out a lot of numbers to the screen, which we don't need. That's because of this I that I put here. Let's delete that, save it again. Let's run prob1 one last time, and we've got the number. Let's make my fonts a little bit bigger here while we're at it. Make it more visible for you guys. Interface language style, default, blah, blah, blah. Command, there we go. 16, go. That's a little bigger. Go 18, and these are all monospace. Well, let's go with this one. Okay, I like that. That looks good. Okay, so this is the answer to our problem. So let me just copy that number 233168. That's the answer to this problem 1, which says we need 5 points for our M file, 5 points for reporting the results. Okay. Oh, and 5 points for code in the PDF. All right, so we got to do a few things here. So let's go here, first of all, where I'm keeping track of my results. And problem 1, 5 points for reporting the results. So if I scroll down here in my code or my source for this document, I can find problem 1. Here it is. Here's where the code goes. And right below that code, I'm just going to answer the sum of um, multiples of 3 and 5 below 1,000 is this number, right? So if I recompile this now, you see I've got my answer right here now. I still don't have my code in here, so I want that. So I'm going to go back to Octave, editor. Here's my code. Just copying that back to Overleaf, and I see where to put my code between the LST listing and end LST listing. I'll just paste it right there. Recompile it. There's my code, and there's my answer. So I need to have a code like this and the answer in that PDF. Or you can type it in Microsoft Word, and that's fine as well. But you still need both of these things in the document. Okay, so that was problem 1. Let's look at the next problem. Let's actually skip that one for now. Let's move on to um, let's move on to problem 3. So problem 3 involves prime numbers. And so specifically, we need to detect if something is a prime number and, answer it. Uh, Answer it. We need to return a 1 if we have a prime number. Now notice that, sorry, I'm getting ahead of myself here. Let's just say what we're supposed to do. Write a function that does this. The input to the function is a number, n. The function will determine if the number is prime or not. The function returns 1 if the number is prime, 0 if the number is not prime. The function should be called isPrimeNum and exist in a file called isPrimeNum.m. And then there is a built-in function that already does this, but you can't call that function because that's cheating, right? We want to write this code ourselves. And then I gave you the start of some code. So I'm just going to copy that. Copying from the PDF like I just did is bad, by the way, because the formatting in the PDF might not be actual, like valid characters for the code. So I'm actually going to scroll down and find the same section of code here. Copy it there. All right. So let's do our new function. So I'm just going to paste that. So this is our function, isPrimeNum.m. I'm going to save it right now. I have to save it with the correct name, isPrimeNum.m. So it's in my folder now. First thing it does is it just detects if you gave it a negative number, and it detects if you gave it a non-integer. So it only works for positive integers. Okay. And then your actual code can go down here. So this is where we actually get started with this function. So like right now, this function doesn't work properly, right? Like if I come down here, if I go is prime num1, nothing shows up. If I do 0, nothing shows up. If I do like a negative number, it tells me that I should have given it a positive number. And if I do a decimal number like this, then it tells me again that I should have entered a positive integer. So the function does stuff, but it doesn't actually work to check if something's prime. So the built-in isPrime does this. So like, for example, if I check isPrime 5, 5 is a prime number, so it says 1. IsPrime 6 is 0 because 6 is not a prime number. Ours should work exactly like this. It doesn't need to work for vectors, it just needs to work for single numbers, and it should reproduce these results. We can't just use this built-in function though, because again, we're trying to write the code ourselves. So a prime number means that the only numbers that go into it are 1 and the number itself. So prime means only 1 and the number itself go into int, right? I'm just writing that as a comment. That's what prime means. So one easy way to get started is you might know that if n is 2, then that's a prime number, right? So what you can do is you can say, actually, let's change this to less than or equal. And then here, if n is 1, 1 is not a prime number, so we should return 0. You don't actually need that semicolon. If n is 2, 2 is a prime number, so you should return 1. I say return 0, return 1. That's wrong. Let me redo this. Y equals 1, because we're returning y. Y equals 1 return. Well, that should be 0. Ugh. And if n is 2, 2 is a prime number, so we should return 1, and then return, end. Okay, so now if we save this, if you do is prime num, first of all, I just made it reject the number 0, which it does. If you put in a 1, 1's not prime. If you put in a 2, 2 is prime. Now, the reason I did a special case for 2 is because it's the only even prime number. So every number that's prime after this is bigger than 3. You didn't actually have to special case this, but I did. Now, at this point, how are you going to check if a number is prime? It all goes down to this fact right here. Only 1 and the number itself go into n. So what we can do is we can just do a for loop like this. For I, we can start at 3 because we already know that, like, if you get to this line, you're already dealing with numbers bigger than 3, right? Because we special cased anything 0 or below and 1 and 2. So everything on line 26 is 3 or more. So for I goes from 3 to n minus 1, that's all the numbers less than n. We just need to check if that number goes into n, right? And we know how to check if a number goes into a number evenly, right? We just did it on the previous function. So we should just be able to say if mod, I keep hitting the numlock key, that's what you're seeing there. If mod ni equals 0, if mod n comma I equals 0, that means I goes into n evenly. If I goes into n evenly, that means not prime. So this is, if not prime, basically. Or sorry, if not a factor, I should say. No, this is if it is a factor. I'm sorry, I'm having trouble today. So this is checking if I goes into n evenly. So that's if it is a factor. So if it is a factor, when I say it, if I is a factor of n, that means not prime, right? So if it's not prime, then we should return 1. Right? So what this code is going to do, I'll take that off. So what this code here, what this for loop does is it just says I is going 3, 4, 5, 6, 7, and you're just going to go, does 3 go to n evenly? That's what this is checking. Does 4 go into n evenly? Does 5 go into n evenly? Does 6 go into n evenly? It just checks every single number to see if they go in evenly. If it goes in evenly, it's not prime. If it's not prime, we should return a 0, sorry. If it's not prime, we return a 0. So we set y equal to 0 because that's the return variable, and then we return from the function. So this loop right here tries to divide every number into n, and if any of them go in evenly, it returns a 0. So if you get past the end of this for loop, like line 33, the only way to get to line 33 is if you're prime. So if you make it here, you are prime. So if you're prime, that's where we can say y equals 1. So you see what we're doing is a for loop catches all the non-primes and sets y equal to 0. And if you make it to the end of the for loop, you must be prime. So we can just set y equals 1. You don't have to say return. You can just let the function end. And there we go. I think we did it. So I saved it just now. So now if I go is prime num. So if I put in a 6, I should get 0. I do. If I put in a 5, I should get 1. I do. Right? If I put in a 7, that's prime. 8's not prime. Well, 9's not prime either. 11's prime. Right? And it works. So do you see this appears to be working? This appears to be working now. And so we got this for loop where we just keep trying to divide everything. So I think we've got our code. Come back over here. So this was problem 3. Problem 3. Where's is prime? scrolling down to find it. There we go. So here's line 169 here is where I've got my function is prime. So I'm just going to delete what's there and I'm going to put in my function, save it. Saving was the wrong thing. I should have hit recompile, but there we go. So now I've got my function in. Now it says show results for running the following code. So I'm just going to take this code here, copy it, come to the command window. I'm just going to copy paste it right here. So I just pasted it right here at the command prompt and I can see the results. So is prime number -6? Rejects that number. That's correct. Is prime number 3.21? Again, it rejects it because we don't allow decimals. We also, if we try is prime number 7, 7's prime, so we should return 1. Is prime number 10? Not prime. Is prime number 77? Not prime. Is prime number 89? That's prime, and it returns a 1. So I'm going to select all these, copy that, go back to overleaf, and it says show the results for running the following code. And I'll just put it right here, actually. Notice that I have like a bad character here. Copy pasting from the command window in Octave often does that. I just look for those and delete them. All right, recompile. And the box goes off the end of the page. That's fine. So I'm showing the results. All right, cool. So I've got the code and I've got the results. All right. Now, I think the problems later on are the problems that people have more issues with. So that's why I was trying to get to these. That's why I skipped problem 2, for example. So let's look at problem 3. We're looking for the largest. Oh, oops. So this text is the wrong text here. So sorry about that. The problem is correct. What is the largest prime factor of the number, this big number here? So let me copy that big number and let's actually find the answer before we do any of the code. So something I didn't tell you guys because, well, I didn't want you to use it, is there's a lot of functions built into Matlab and Octave that do stuff like this already. So for example, there's a function called factor, and that does prime factorization. So if I do like, let's say 20, for example, factor 20, you get 2, 2, and 5, right? Because 2 times 2 times 5 is 20. So that's actually the prime factorization of 20. And if you go back to this problem here, it says, what is the largest prime factor of this number? So if you factor this number, which I guess I missed a 6 at the beginning, if you factor this number, those are the prime factors. So what's the biggest one? Right here, 6857. Okay, so that's the answer, 6857. But that's kind of cheating to use the built-in MATLAB prime factorization. But you could do it to make sure you know what the answer is. So that's prime factorization. And the biggest prime factor is 6857. So we have the answer. That's kind of cheating. Not really. It's not really cheating because I didn't actually say you had to not use that function like I did for the previous problem. So, that would have been okay. But for results, you must actually tell me what the largest prime factor of that number is. Well, we know it. But let us try to write code to do this. Now, there is a pretty easy way to do it. I say pretty easy way. Let me make a new script here. So let me save it as, this is problem 4. Not in. Yeah. So there is a pretty easy way to do it. Like here where it says the prime factors of 13195 are 5, 7, 13, and 29. Let's do this as an example. Um, n equals 13,915 is 13,195. Okay. So there's actually a pretty easy way to do this, but it's slow. So what you can do is this: make a for loop, right? Um, yeah. So you can make a for loop, and then you can say for I goes one, actually not one, start at two, um, to n minus one. So we're checking every single number bigger than two. And then what you want to do is um, if, well, first we can check if the number is a factor. So to check if the number is a factor of n, if I is a factor of n, you do if mod uh, n comma I equals 0, right? That would be checking if I goes into n evenly. So that's is a it's I a vector of n? Yes. If yes, if is prime I. So look at what we're doing. Every single number from 2 up to n, basically, is the number a factor, and is it prime? So if it's a factor, and if it's prime, then you get here. Well, what are we supposed to do with it? Well, we're supposed to be finding the biggest prime factor, right? So like if I make like a list, like prime list or something to store my prime numbers in, I can just take the prime list int plus one. That puts something at the end of the list. Actually, I don't want to do that. Hold on. I'll do it this way. Prime list. And if the number's prime, let's put it at the end of the list, right? And so this for loop right here is going to find all of the prime factors, right? And in fact, if I do display prime list at the end, let's see what this does. So we're going to run prob for, and it says 5, 7, 13, 29. 5, 7, 13, 29, right? Those are the prime factors of this number. Okay. And now, of course, if you have the list, instead of displaying the prime list, you could actually do the maximum, right? Max prime list. That would be the maximum entry of that list. Now, looking at the command window, something you might notice is that they're always going to get bigger. So the last one is always the biggest. So you don't really need max, but if we do a max, it's fine. So if I run this, it works, 29. Great. Now here's the problem. If I put that huge number, this number right here, 6, save it and go to run this, 4, you notice I don't have an answer yet, right? And in fact, we can let this run for a minute or two. Well, I don't want to wait that long, but while this is trying to run, it's not going to finish anytime soon. And in fact, I don't know how slow it's going to be. So I don't really want to wait here to see if it gives me an answer. Like the fan's kicking up on my laptop, we don't have an answer still, and so on. So I don't really want to use this code. And so I'll stop this code from running by hitting Control C. We still don't have an answer. So this code works, but it's not fast enough. Okay, so what I want to do is change this to have a chance of working. So let me go back to the small number first. And we need to change this for loop to something else that works faster. So here's the thing. I don't know if I can, maybe I'll open Notepad or something. Notepad. That's Notepad++. That's not what I wanted. Oh well, I'll just do this here. So here's the thing. If you have a number, like let's say 500 or okay, 5,000, that's what I typed. So if you have 5,000, right? When you find a factor, like let's say you check if like 2 goes into 5,000, right? So 2 goes into 5,000. So this 5,000 splits into a 2 and a like 2,500, right? So what happens is if you're looking for prime factors, you don't need to go up to 5,000 anymore. You only need to go to 2,500, right? And what that means is that every time you find a factor like 2, you could actually do this logic. Like, let's say we start with, let's start with the number that's here, like 13, 9, start with this number, for example, right? So you look for the first factor, which was 5, I guess. No, was it? Hold on. Let me factor. What's this number? Yeah. Oh, yeah, 5. So the first number is 5, right? So our for loop is going to find that 5 first, right? So 5 goes into 13195. Well, then what you can do is you take that 13195, divide it by 5, and then now you have 2639. So you don't need to be dealing with this huge number anymore. You can just deal with 2639 and look for factors there, right? Like when you factor by hand, that's how you do this, right? Like you would be doing 13195 splits into 5 and whatever it was, 2639. And then to continue on factoring, the 5's done, you just factor that 2639, right? And the 2639, apparently a 7 goes into it. 2639, 7 goes into it. So that factors into a 7 and 377, right? And then the 377, apparently 13 goes into that. 377, 13. I'm getting those just from this list here. So 377, 13 goes into it. So that 377 is a 13 and a 29. And then that's it. And so this prime factorization process keeps dividing these numbers. And that's how the numbers get smaller. And that's how it runs fast, even starting from a big number. So we aren't doing that right now. So we have to change our code to do that if we want our code to run fast. So basically what we want to do is instead of a for loop that goes from 2 to n-1, which is going to be too big for us to run, let's change it to a while loop. And we can do a while loop while I think we'll just do this while I is still less than n. I think will work. Okay. And then what we're going to do is this. So instead of looping from, so remember how it was? It was like this. Instead of doing a for loop, I'm going to replace the I. I'm going to calculate the I myself. So like, let's start I at 3. Actually, let's start it at 2. That's fine. No. Yeah, okay, that's fine. We'll start it at 2. Then we'll do a while loop while I is less than n instead of a for loop. Inside of this while loop, we need to do the exact same stuff. So we still need to check if mod n comma I is 0. And we still need to check if it's prime. Okay. But after we do that, we should add it to our list of primes. But the other thing we should do is not just add it to our list of primes. we can take the n and we can divide it by I. That's the equivalent of what we're doing here, like 13195. Once you find the 5 that goes into the 13195, you should divide that by 5 and you're left with this. So like this is our new n value, 2639. Sorry, trying to get back to, oh, I was already on the editor. So you can update the n value like this, and then you can keep going. Yeah. But the other thing you need to do is you need to update I. So because we're not doing a for loop now, you have to control the I yourself. And so if we just keep doing this, eventually the number I will be bigger than the number n, because the number n is getting smaller and the number I is getting bigger. So our basic code for checking if it's for checking for prime factors still works, but hopefully this runs faster. Let's find out. Well, let's find out if it even works. It says 13. So it didn't work. What's our prime list, by the way? Prime list. So it found the 5, the 7, and the 13. It didn't get the 29. Why didn't it get the 29? Oh, because it didn't get the 29 because it did not get the 29 because it left the while loop. So I think the way we can fix that is if I put this at the beginning. And notice I'm doing all my testing with this smaller number here rather than that huge number. So I put this at the beginning. Let's see if that will pick up the 29 now. Oh, wow. So really sorry about that. So my microphone just fell. So that's going to be really loud, and I don't think I can cut it out. So apologies. I'll find it and I'll warn you. All right, back to what we were doing. Octave. Okay, so I think we run it again. Oops, let's run our code again. Oh, and now it just works. And if you check the prime list, yeah, so that's the correct list of primes. So this works. Now, there's other optimizations, like I is going up by 1, which means we go 2, 3, 4, 5, 6, 7, 8. But there's no point in checking there's no point in checking even numbers, actually. So you could actually go up by 2s, and that would be fine. But if we go up by 2s, then you have to change this to 3, and then you only count up by odd numbers, 3, 5, 7, etc. You never need to check an even number because even numbers aren't prime except for 2. But let's leave it like this and see if it runs fast enough. So we'll go here. Let's get the big number. Let's put the big number back here. Again, it lost the 6. And let's see if this runs fast enough now. That's not it. Let's run the code. Oh, look at that. We got the number. And just to remember, I'm scrolling back. If you check the factor of this, 6857 is the correct answer. So do you see how our first code with the for loop didn't work because we had to check 2, 3, 4, 5 up to this number, which is humongous. But when we add this, basically this line right here, n equals n over I, saves it because this number now gets smaller. It doesn't stay up at that 6 huge number. All right, so this code works, and I think it's fine. So we'll just leave it at that. So this one line is what makes it run fast. All right, so we did that. Oh, we need the code, so let's I'll condense it here like this. Copy that, save this. Go in here. What is the largest prime factor? So we'll paste the code in between the listings. And then it says you must actually tell me what the largest prime factor is. We know it. It is this number. So largest prime factor is that. Recompile that. There it is. Now, also, you'll notice that in my right up here, there's lots of blank space now. Those blank spaces are caused by new page commands in here. So like if I do Control F and I look for new page, like there's one right there. I can delete that. There should be one up here somewhere. Go up to the top. Next. Yeah, one on line 155. Let's get rid of that. If you delete those, then it won't start new pages all the time. All right, so we did 1 and we did 3 and we did 4. Okay. So we got 5 and 6. So 5 and 6 are more finding prime things. Yeah, so these are all just finding primes. So how do you do it? Well, basically, we know how to find primes, right? If you wanted to find the first, like if you want to find 10,000 prime numbers, it's very straightforward. I think very straightforward. I think we can do that in just a few lines. If we go here, so what are we doing? We are find the, I'm not gonna like 10,001 first prime. So here's how we can do it. Let's so first of all, let's put a number in. Now this should be like 10,001, but like for starters, let's just do like 5. Or actually, let's look at this. The first 6 prime numbers are 2, 3, 5, 7, 11, 13. The 6th prime is 13, right? So let's just change this to 6 to start with. Okay, now how are you going to find the 6th prime? Well, it's really easy. Just do this. For I goes from 1 to, oh, actually, no, don't do that. So like set I to be 2, right? 2 is actually the first prime. But then what we're going to do is this. While prime, let's do another like prime list like we did last time. So we're just gonna store all of our primes in here. And then what we're gonna do is we need to make a list of primes until the list gets up to 6. So you can say while the length of the prime list is less than 6, do this. Now in here, what do we have to do? We're gonna have to calculate prime numbers. So all you're going to do is this. If I is what I'm using to, for the number that we're testing right now. If I is prime, right? So if I is prime, what should we do with it? We should put it in the list. Prime list equals prime list I. So that just puts I after the prime list. Okay. And then what do we do after we check if it's prime? Well, after we check if it's prime, I needs to be I plus 1. And so we're just going to loop through here until prime list has 6 things in it, and then it will stop. So I'm going to save this. What problem is this? Looks like 5, prob 5. So save this. Let's see if it works. Uh, prob 5. Well, I don't know if it works because I didn't print it on the screen, right? Prime list end. So that's just to display it on the screen. So let's run this. Answer 13. Yeah, so that works now, right? Because the 6th prime is 13, right? So if I change this to a 5 and run it again, right? Prob 5, it's going to tell me 11. Oh, it didn't. Why didn't it? Did I save it? Okay, so something's broken. What's broken? So, oh, I see. I hard coded the 6 here. This should have been in. Save it. Run this again. Okay, now it works, right? So the 5th prime is 11. If I change that to a 6, it'll give me 13. So now if I just go 10,001, 10,001, this should work. Now, is it fast? I don't know. It might be slow, but we're still going to run it and see. While that's running, you can look these up, by the way. So if I go here and I just say list of prime numbers, 1 to 1,000. Let's see. Actually, let's do this. 10,001 prime number. So a lot of people have done this problem before. You notice that you see a lot of references to Project Euler because that's where it is. All right. Well, that's not. I clicked on the wrong link. 1 to 10,000. All right. Well, that's almost there. Anyway, that's not important here. Let's. You can look it up if we cared. We don't care. What we do care is that we found it. It took a little while to run, but this is apparently it. And if you look at the length of your prime list, right, that's a variable, 10,001. So if you take prime list 1, there's the first prime number. Prime list 2, there's the second, third, fourth, right? So if you wanted the like 999th prime number, it's apparently 7907, right? How do we know? Because we just calculated it, right? We just went through and we actually calculated 10,001 prime numbers. We didn't do it in the fastest way, but we did it. So there we go. So the answer is this 79. Oh no, it's not. This one, 104743. Whatever that is, I'm scrolling down to it. That was yeah, this one. So I see it. So the answer is the 1001 first prime number is there. So there's my answer. And then my code is here. Okay, so you see this is working out fine. So your last problem here, I skipped I think 2 of them. So for your last problem here, we want the sum of the primes below 17. That's very similar to the code that we just wrote, right? Except that this right here calculates 10,001 prime numbers, right? If you want to do this, like let's say find prime numbers below, like, I'm just going to say like 1,000. This is just a made up thing. First of all, I should save this as a different name. So like prop 6 or something, right? If you wanted to do this, this is a different problem, right? Because we're finding prime numbers below a specific number like 1,000. You can still do this exact same way, but uh, you don't go until the length of the prime list is less than n. What you do is you go until the prime number or the potential prime number, the I, you go while the I is less than n, right? So it's not the how many prime numbers there are, it's how big the prime numbers are now. So you change your while loop to be this. You can still make your prime list like this. And if I just do this right here, actually, let me change this to like 10. Um, so all we did was we just changed this one line and we changed this n equals 10 thing, right? If I go prob 6, let's see what it does. Prob 6, if you look at your prime list, 2, 3, 5, 7, right? Isn't that all of the prime numbers below 10? It is, right? So just changing that one line is going to be able to calculate prime numbers below a certain number. Um, but what we want to do is we don't actually want to store them in a list. And the reason you don't want to store them in a list, let me show you. Um, there's a whole lot of prime numbers below 2 million. So you don't want to store them all probably. Probably we just want to add them up, right? Because it says the sum of the primes below 10 is this. Find the sum of all the primes below 2 million. All right, first of all, let's just check if this is working. Um, I think this should actually be in -1 again. Wait, no, it should be less than n. You have to be careful here, right? Because like if I put like a 7 here and I run this, and then we look at the prime list. Oh, okay. While I is less than n, I put an 8. Okay. Yeah, okay, I guess it's fine. So this code looks like it's working. It's calculating primes, but this is not what we're supposed to do. We're supposed to be adding them up. So just make a total like this, s equals 0. That's like your sum to store the sum. And then we don't need this line at all. What we need is if it's prime, add it to the list, right? And then you display your sum at the end. So I just ran it and the answer is 17. So if you change that to 2 million, it should work. Like, but I'm not going to. You can do that. So if we wanted to add up all the prime numbers below 100, it's apparently 10,060. Sorry, 1,060. All right. So I think that is all I want to do. I think I did most of your homework for you, but that's okay. And sorry for the loud sounds. I can't mute that, so it's just going to be there in the video. All right, so that's it for now. I'll talk to you guys later.